Hello, everyone. Welcome to our webinar today. The topic is introducing RisingWave Ultra. So this topic is a little bit more technical than the previous webinars we've done. It's a brand new edition of RisingWave that we are introducing. So in this talk, I want to talk a little bit about what RisingWave Ultra is about, what is the motivation behind it, and then and have a demo at the end. Um, First, some housekeeping items in terms of these are regular rules we employ, which is to, have the mics muted during the webinar so that everybody has good experience. While the mics are muted, but you still have access to ask questions because we want to keep it interactive. So encourage you to post questions as we go through the webinar, and we'll answer them at the end. But there may be others on the team who might answer them while the webinar is going on. We will record the webinar and have it posted on YouTube, so it'll be available for you to watch later if you want to. And then if you have any issues with connectivity or Zoom in particular, you can use the chat to reach Yovana, and she will be able to address any questions you may have. Um, Quick intro. I mean, probably you're probably familiar with my background, but just to reemphasize, my name is Rayees Pasha. I lead the product team at Rising Web Labs. Primarily, my experience has been in the database management and stream processing technologies. Started as an engineer working on a database optimizer with Hewlett Packard. It was a product called Nonstop SQL. It was a relational database. And then I moved into product management positions at different companies, primarily in the data infra space itself. So in a way, I've seen sort of the full spectrum of how technology has evolved in the data infra space from really traditional relational database to NoSQL, big data, the whole big data movement, and then now coming back to Rising Wave, which is sort of a combination of old and the new, where we're still a SQL database, but under the hood, we're a modern database in terms of how we process the data and all that. Um, in terms of this is yeah, I went over this in the previous two editions of the webinar. The current talk is part of this Rising Wave Rollout Month series. Rollout Month is something that we embarked on this year because if you have features that are larger than a simple feature that can be expressed in a few minutes, a full-blown webinar kind of justifies it. So that's how we came upon this concept. This is obviously one of the ways we reach out to our community to interact with them and provide product updates. The idea is obviously to increase engagement with our community. So even after this series is over, obviously you are welcome to join our meetup group and participate in our community activities in terms of ongoing webinars, meetups. And if you're a user, I encourage you to join our community space on Rising Wave Slack. That's the best way to learn about Rising Wave. If you run into issues, we have on call who can answer your questions, and then you can learn from each other also, from other groups, other users who may be posting questions on how they are using Rising Wave. And as I mentioned, this is last in the series of the webinars we embarked on. First, we did Rising Wave Connect, which was last month, and then Open Lake, which was to do with Iceberg. And then today, Ultra, which is more performance focused. So the agenda is, as I mentioned, quick introduction, followed by some background and motivation of why we embarked on this. And then the internals, this is the part that's gonna get a little technical. I try to keep it light, but yeah, the changes, the enhancements that we've added are all on the internal. They're not user facing. So just wanted to give you a little bit of demystify all those things. And then we have a demo, which is um, we should take about 15 minutes. So it takes time to set it up. So I'll try to allocate enough time so that we go through demo and then finally some questions and answers at the end. Um, if you are new to RisingWave, maybe I can spend a minute just to explain what RisingWave is. If this is the first time you are with us on a webinar, RisingWave is a streaming first unified data processing platform. Like by that we mean the heart of it is a distributed SQL streaming database. So think of us like a hybrid category where we are combining incremental processing stream processor along with a full-fledged database system, like a distributed database system, right? So in how it's used is as shown in this diagram, where we are right in the middle of a data pipeline, where if you have data stream, upstream data coming through message queues or CDC streams or even static data sitting in a data lake, for Rising Wave, the data model, those streams are just like base tables, right? From a data model perspective, you consume the data, you ingest, you process in an incremental fashion. You basically have streaming jobs set up that continuously process the data as it arrives. And as part of the processing, you can perform any of the transformations that you typically do with regular tables, like a SQL tables, right? You can filter the data using standard predicates. You can do aggregations. You can do joins, multi-way joins. So even if you have streams that are like 10, 12 streams coming together, you can join them. You don't have to worry about how to maintain state and all that. The system is smart enough to figure that out. And once you process the data, you have two options. You can store the data as rising wave tables that goes into row store, which is typically well suited for low latency serving applications. Like if you have like real time, like from a data latency perspective, that would be the way to go. But we also offer you open data lake format, which is Iceberg, where you can store the data natively as Iceberg tables, which tend to have higher latency thresholds, and those are great for analytics use cases, right? Our focus in today's talk will be on more on the low latency side. So we had dealt with the Open Lake in the last webinar, so you're welcome to check out that webinar if you're interested. All in all, our guarantee is in terms of freshness, latency, which is sort of our core competency. Because of the incremental processing model, we can guarantee freshness under a second for even complex pipelines, right? If you have multi-stage pipeline with complex transformations feeding one another, we can still guarantee the kind of freshness because of the fact that the paradigm of how we process the data is very different from a batch processing model, right? And if you have even latency requirements of P19 and up to under 100 milliseconds, even for complex workloads, and which is what I'll try to showcase in as part of the Rising Wave Ultra. Okay, now let's talk about the introduction of Ultra itself, right? So Ultra is, as I mentioned, is a performance enhanced profile of Rising Wave. So the way to distinguish is you have the Rising Wave core, which provides all of the table stakes needed to process the data in a streaming fashion. Now, where RisingWave Ultra comes in is with some optimizations purpose built to allow for very highly like extreme low latency use cases, right? The basic objective is here to integrate best practices that we have picked up working with customers over the past year, 2 years, right? And apply those performance optimizations, which were specific to one customer or one workload across, and try to have the collective knowledge that we have accumulated over time. Another objective is to keep the binary consistency, by which I mean you don't have a separate product called Rising Ultra with a separate binaries, right? It is the same single binary, single code base, the same code repo that we have, so that users are not tied into, like, once you go use Rising Ultra, you are using a different product with a different licensing model, different. No, we want to keep it same. It's just a optimization layer on top. From a value of proposition perspective, your primary core concern here is performance, right? You are building something that is customized to a particular business problem you're trying to solve, right? And then from a product perspective, like I said, again, we're not trying to we're not trying to fork Rising Wave into a different, as a separate add-on product. It's more the product integrity is the deployment model that you are used to currently will all be supported. In terms of the benefits to the customer, obviously the performance enhancements are really the key driver here. And your solutions, basically, whatever, if you have a hard problem that you cannot solve with out of the box with either with RisingWave or with other systems, that's when we come in. Like here, this is not simply a product approach here, more like a tailored solution approach, right? So it's a little different in that in the way how we deal with it. And our help to you is not just on the product feature level. It's also about the guidance, how best to solution architect a particular solution, given your demanding requirements you may have, right? The idea being that it is a combination of a consultancy as well as your product support, right? So it's a little bit of a different model. So how would the engagement model look like, right? So typically what we do is we do a deep dive of your solution, your problem, and then propose optimization techniques. What architectural improvements or optimizations would make sense for this specific customer workload, right? There's different things that are there. Not all of them apply to everything. So in a way, it's a very different engagement model. We typically ask customers some basic questions, when you are exploring RisingWave. In this case, you would go a level deeper. Some of the things questions may be about memory utilization or a specific transformation you're performing, the kind of SQL you are running with core, RisingWave core, that where you are seeing some performance issues. So in a way, it's very subjective, right? And by design, it's a high touch model. It's not going to be lightweight where you just leave it for the customer to fend for themselves. It's more like work closely with a solution architect. And obviously, it's a partnership. It's not simply a customer versus a vendor. It's because you are building sort of a solution, uh, like almost like a bespoke solution in some sense. So it's a partnership approach from that perspective. Now, why did we, I think from a background, the question that we get is why not Rising Wave core itself? Why do you need to have a something thing, right? So before we answer that question, it might be good to get a sense of the background, like why, how do we arrive here, right? The core requirements for building incremental data processing in general for a stream processor at scale, there are set of requirements. Like for example, one of the things you immediately encounter is the massive intermediate state data that any streaming workload will get. Like for example, if you have a very simple example here of a e-commerce application where you're trying to process data as it comes in after the sales have been completed. As you can see, there's multiple joins from various sources coming in and a lot of processing that's happening in a multi-stage pipeline, right? So this uh, can get really uh, complex in terms of how much data it'll accrue, right? It'll go into dozens of terabytes of data if you have even a moderate size of source data coming through. So your stream processor need a way to handle a massive state and hold it in memory or hold it in a way where it's easily accessible. And also the fact is, having a simple local deployment or a single server deployment will no longer suffice. You need to have more cloud native deployment to handle that kind of scale. Third thing is you need to be able to have a good way to manage the IO throughput and the cost. So you don't, it makes sense from a cost perspective that it's not cost prohibitive in that sense, right? And then the last thing is, um, for any incremental data processing at scale, the throughput is not uniform. There is going to be spikes going up and down. So we need the stream processor need to be able to handle, and perform under pressure. Like when there is a sudden spike, be able to gradually and smoothly handle those spikes, right? To build all these, that's why we didn't take a existing solution. We built a purpose built storage engine for these kind of requirements called Hammock, and that's been there with us from day one. It addresses any issues with the high velocity data that we get from a stream processing perspective, right? um, Now, Hammock has tiered storage built into it. So you have a latency hierarchy, right? Which is where a lot of the issues come from the perspective of freshness, right? The typical hierarchy is you have memory, you have disk, and object store. That's the hierarchy. Memory tier is obviously the fastest. It allows for the highest bandwidth in terms of usage, and it's in how what we store in memory is what's called operator cache. That's dedicated to each operator. Could be a aggregation operator, a join operator, things like that. So it's very specific to a job, and within a job, a particular operator, right? So it's because we don't want to within a job to the access on processing that particular operator's requirements kind of become trump everything else. And then we have disk cache, which is intermediate, where you store data in a serialized format, so it has a slower performance. And obviously, object store, which is our persistence layer, that happens to be the cheapest in terms of cost, but the reads can be expensive because the round trip to go through the network, you know, uh, can really slow things down. Now, this is important because these trade-offs are what dictate providing user a cost versus performance, trade-offs when they deploy on Rising Wave Core, right? They can make a choice whether if they can live with certain freshness, they sacrifice performance for cost or cost for performance, right? But with what we have seen with newer applications like like for example, in terms of motivation for Rising Wave Ultra, there are some latency sensitive applications like trading, fraud detection, things like that, where that trade-off doesn't work. You really don't care about the money, you care only about the performance, right? Because um, the assumption is time is money, literally. Like for example, if you have a crypto trading dashboard, um, it makes no sense for them to have anything but like real time performance, right? So because the decisions are made by algorithms, not by humans, so it's almost like you have to have sub-second, sub 100 millisecond sort of response consistently, otherwise you have bad user experience. And it doesn't make sense because you have a competitive disadvantage from a business perspective, and that's true for even other use cases like credit decisioning, network security, and things like that. So what was our observation when we dealt with these kind of applications? One is IO is still the primary bottleneck, right? How do we reduce that? Like that is the primary source of latency spikes. So how do we address that? And then the second thing is how do we use memory? The better we use memory in terms of optimizations, the closer we are to ensuring consistent low latency, right? Using memory judiciously where it's not required to reduce the usage versus using it right? So it's almost like we are hyper tuning caching. In a way, it's a core requirement, right? And the third observation was, which is basically users are willing to allocate extra resources for higher value application, right? Typically, when we estimate cluster sizing with Rising Wave Core, we try to tend to find cost considerations in mind when we make a recommendation. With this, we are basically saying the cost considerations are secondary. So in a way, the approach is to provide lowest possible latency with more than sufficient resources. Say if you require X, let's go with X plus 20% or whatever it is, just because we want to have that extra headroom, right? So that's sort of the observations we saw, which kind of dictated how we want to design Rising Ultra. So as I mentioned, the issues to solve are primarily around current caching model, right? The issues that really affect caching from Rising Wave in core is one is the let me first explain, like block cache is something that we have from a disk perspective. That's a feature that we enabled a few months back. Now, that gets affected each time there is a compaction. Like whenever there is a compaction and if a read happens, that will invalidate block cache, which means all of the data that was stored in block cache needs to be reread. And that causes obviously um, additional overhead in terms of um, reading from remotely from the object store, right? So that's one problem we saw with inefficiency in the current caching model. Although it solves some problems, block cache, but in some other ways, obviously, it's causing an issue. And then the second thing, what we call metadata cache, which is maintained and it's filled automatically. But sometimes what happens is whenever black block cache refilling is happening, it affects meta cache also. So in a way, by having block cache, which is a great way to reduce the cost, overall cost solution, it introduces additional latency for certain applications. And then there's other factors that also affect caching. For example, the just the serialization, deserialization of data, because you have multiple copies. You have a main memory, you have block cache, and you have the object store, which means there's a different format of each, how we read and write. So that introduces additional overhead, and that actually creates contention in terms of logs. So all of these things kind of are great in some sense for Rising Wave Core, but for extremely low latency sensitive use cases, they introduce inefficiencies, and those need to be solved. Now, how do we do that? Um, the way we do that is by uh, discarding the use of disk cache completely. So you have only main memory operator cache where we store all of the information, and then the rest, obviously the persistence layer happens to be the object store. That doesn't, we checkpoint and we store the data there. That doesn't change. By using exclusive user operator cache, we obviously have fastest access to all of the information, right? No need to check for Bloom filter data files when we need to see if there's a particular uh, date per part of data is there or not, right? You check for memory and you're guaranteed to have it in memory, right? There's no lock contention so it means that you get a single threaded access to operator. And then last but not least, the serialization, deserialization um, problem that we have, where there's compute overhead, that's also removed because everything is stored in native in-memory structures, right? So all these improvements uh, shave off a lot of the time it takes for us to do the processing on the fly. Besides just using operator, there's other aspects also, right? We're not just saying, because then we would be no different than an in-memory database that's which have been around for a long time. In a way, we are still a hybrid. So where we give users choice to configure the state storage, where you can be selective about what you store in memory. Like for example, specific operators. Like if you have multiple workloads running, and within those workloads, if you have a specific operator that you care most about, like for example, if you have a aggregation perform or a window function, which is very resource intensive and is the operator that was causing latency issues, you can actually pick that particular operator to reside entirely in memory. The rest of it can use disk cache. So in a way, it's not a one approach for all. That is the kind of tuning control knobs we are going to provide with Ultra. And that's also the reason why you need to work with us in a way, in an engagement model, that some of those internal details are not really something that the end user, at least a beginner user, can understand, right? So that's one of the reasons. And also, obviously, we have added temporal locality to avoid having to have remote access. That's another thing. And then the last part, in terms of performance control, I mentioned offload the part of the state that is no longer that is less critical to disk cache. So you can balance the cost and speed. That obviously remains as one of the options. One of the questions that obviously people would ask is like, if this would mean my memory usage will increase perpetually. What if we go beyond the memory capacity, right? Because that's a valid question. Even if you have unlimited budget, the memory capacity in terms of procuring resources could be a challenge. So the default option is to fall back to Rising Wave Core, where you say, I don't want to use Rising Wave Ultra because I can live with for the temporary for maybe at a still if it goes beyond a certain limit, which is the default option. But there's other ways, like you can use database isolation. You can create resource groups where you can put queries, specific queries. Earlier, I talked about isolation at the operator level, which is very, very. granular. But you could also do like, if at a course level, if you run out of memory, you can say these are the few jobs that I care most about, and then start putting them in particular resource groups so that we know those, and you can increase the capacity and allocate more of your available memory to those users groups so that they don't get starved. While there may be another query that you feel like it's less important, I can I can live with the less fresh data there or higher latency there, right? So this is another option. This is an existing feature already there in RisingWave Core that can come in and help you if you run into issues with RisingWave Ultra. Um, in terms of the another aspect that's critical also with Ultra is how do you handle the backfills, right? Because whatever we talked right now is about ongoing processing that continues, right? But there may be massive backfills. Like for example, if you have Solana data in crypto cases where you have to load, or if you have historical e-commerce purchases, you have terabytes of data. Obviously, the model that we have earlier, which is in memory, doesn't work, right? You can't hold terabytes and terabytes of data in memory to do the backfills. There, obviously, with Ultra, you have the ability to prioritize throughput over latency, right? You basically relax all the conditions you imposed on the stream processing during the ingestion phase so that you almost run as if you're running Rising Wave Core in terms of backfills with disk cache and all the safeguards you have. And you go past that, and then you go back to the total in-memory mode. And how we and there's other improvements that we have done into the product to improve historical data processing. Like for example, we used to the one of the common problem was poor data locality, where historical data would be spread across, so you would have to do remote access and random access. That will really hurt. So some of those improvements we have added, they will benefit both Rising Wave Core as well as Rising Wave Ultra, but it really helps with that random access pressure. And also in terms of during, if you have high level of state already built in during the backfilling process, there are ways to uh, you know cap the limit of how much CPU memory network usage, and without really causing stability issues, right? There's some knobs that we have introduced, even for, we call it the local backfilling optimization. That feature will come out fairly soon in 2.7. That will help for this problem as well. Yeah, I think it covered some of this, like for example, reordering the data on the fly, similar to indexing for backfills. Compaction aware, this is the part about ensuring capping resource level so that you don't um, go overboard. Like in fact, this is one of the feature that allows us to use our existing capability to do serverless compaction so that you can cap the compaction at a certain level, and then anything flex capacity, you address it through this serverless compaction service. And also, if a more aggressive pruning of the temporary data that's created, all of those do help. So this, I think we are at the halfway mark, so I want to make sure that I do have a time for demo. So what last before I go to the demo, let me talk a little bit about the ongoing work. Like with Ultra, what I want to be careful is it's not a one-off where we build one feature or two features and leave it, right? This is going to be an ongoing exercise. We're going to add more and more features to make this even more powerful, right? And some of the things we're doing is um, so far the problem that we have tried to solve is the I/O, right? We feel like storage engine as designed is great for traditional stream processing use cases. For extreme low latency, I/O is a bottleneck, so let's address that. That's what we've done so far. But there may be cases where I/O is not the only bottleneck, or may not be the bottleneck. In such cases, how to tune CPU so that you use the parallelism in a very intelligent way, right? That's one of the things that we are working on. Second is we are trying to reduce the memory footprint itself, like avoid having duplicate memory copies so that make the zero copy access the default everywhere. That's another key area that we're working on. And then third thing is configurations themselves. Like right now, a lot of it is, as I mentioned, on a per workload, you have to generate optimal settings for each and test and reiterate over it, and then kind of get to a particular sort of a custom solution, right? Um, what if you bring in new workloads, have the system auto tune as much as possible so that you don't have to do this manual exercise, right? Now, how do you generate those configurations based on previous tuning and so that you can apply them, right? That's also another, it's more from an operational perspective, how to make this repeatable so that every time you don't have to start from scratch, right? So that's another area of focus for us going forward. All right, so it's a demo. Let me quickly talk about what the demo is going to be. So the demo is basically we have a high throughput aggregation query from a real world crypto exchange use case. So crypto exchanges have these leaderboards of all the items that are being traded, and the prices and the quantity that is traded gets updated in real time, right? Like, and people place bids based on that real time information, right? And so the dashboard should reflect it in like really milliseconds, because if a user logs on to multiple exchanges, if they want to get the best price, they want one that is truly reflective of the immediate what the price is, right? So in a way, this is a classic use case where you're dealing with data that is fast changing and changing in like really micro milliseconds, so for this use case, the simplified use case, we put it in this GitHub repo. I'll be using this to drive the demo. In terms of hardware, we're using EC2 instance with 64 cores. And for both real RisingWave standalone, standard and ultra, we're running the same setting. There's no change between the both, and they both have more than enough memory, right? And we're using RisingWave version 2.5. We fixed the degree of parallelism 32. We're using Red Panda as the message queue to bring in the data, like all of the data events that are generated. We're using Red Panda just as a message queue. Okay, let me stop sharing and I'll share the screen to. So I'm running, as I said, I'm running it on a EC2 instance. So I'm going to first connect to that EC2 instance. Um, so first thing I want to do is make sure that my database is done. Okay, so it's not running. So I'm going to actually first let me, oops, I have to go to the right directory first. Okay, demo directory, and then if I go to the TOML file, there is this new variable that we have called stream default enable memory preload. This is the one that tells system to use RisingWave Ultra, so that preload everything in memory so that you avoid this cache, right? So that's set to false, which means right now we're in RisingWave core mode. Okay. So I'm gonna create my database. Uh, okay, sorry. Okay. So the now database is created. Now I'm gonna create the objects. I have a script called Python RWPI. So it'll create it'll create the source. It'll create the sink to read from the upstream Red Panda source that generates the events. Okay, and I'm gonna start this consumer that'll read from the source, and I'm on a parallel window. What I'll do is I'll run the producer. So this is another session I'm going to open on the same EC2 instance, and I am going to run the producer here, which will basically generate, it'll run for a few minutes. Sorry, it's okay. Here's the producer at PI. So this, okay, sorry, I made a same mistake here. I got to go to the right directory and then I start the producer. So the producer is generating 100,000 records, like each event in a batch, and basically it is creating it, like if you go to it'll it'll basically create producer PS generating events and send them to Panda, this the Python program, and each of the event has a timestamp associated with it called a starting timestamp, and then it goes through the processing and does the aggregation, and then we sync it back to Red Panda, and we call that the ending timestamp. The goal is to measure the latency from the starting timestamp to the ending timestamp and make sure that the latency of that is below a certain threshold. Now we're running this with RisingWave standard now, and we'll capture the dashboard of what the latency looks like for the 5 million records. Actually, we're going to load 5 million records here. And then we'll do the same thing with RisingWave Ultra and we'll compare them both in terms of what is the latency in terms of P50, P90, P99, so that you can see what is the difference in terms of performance. So yeah, it's running it. First, it is producing records, as you can see, up to 5 million, and it'll stop there. And then the consumer will start, like consumer is already in parallel. It as the producer generated, the consumer is now going through and reading into RisingWave. It's going to take a few more seconds, and then you can see the as you can see here, and with standard, if you see the latency P99 is going up to 3 seconds, you can see the latency of how fast those events are being processed, right? You will see obviously an order of magnitude slower with Ultra once it's right now it's going over a second, like 3 seconds at this point. Almost there. Okay, it finished. So it should clean up and the program should stop now. Okay, it's the final statistics, as you said, it's telling you all the batches it used. It's gonna have 500 batches, sorry, 1,000 batches, and then it'll tell you how what is the throughput. Like as you can see, the throughput is variable. It goes up and down. So it goes all the way throughput to three. I saw more than 300,000 to 150,000 records per second. Now we have done the producing, we have consumed it, and we have calculated a bunch of metrics here. We've gone through the so just to walk through the steps, we we created the source, we ran the consumer to wait for the input data. We generated the input data through producer, and now we have after all of those are consumed, it'll create what's called latency stats. And that's what I'm gonna fetch that latency stats to my local machine and plot the data using this program. So let me bring in the data now. I'm gonna copy it to my local machine. Okay, so it brought the data. Now I'm gonna plot it using this program. Okay, as you can see now, for this particular was standard, it started good and then the latency kept going up. It gained the high water mark, like for P99, it went up to all the way to 8 seconds, 8,000 milliseconds with 8 seconds, right? And then it kind of fell slowly. And in terms of the throughput also, it was highly variable, right? It went as low as 100K and then higher the better, obviously. So you can see the throughput went through high, but then obviously the reason why it went high is because the latency also suffered, right? So you see the correlation in both. Um, and then if you go a little bit more into details of how latency wise, see, as you can see, the P99s are going through. There's a lot of high concentration at the. There are some long tail latencies that you can observe, and then in terms of the throughput, this is more reflection of what you saw earlier. The same way. And then the stability for basically from P99 to 90 in terms of spread, as you can see, um, there was a huge spike, and then it stayed pretty much throughout. So in a way, the performance, it seems like in the install warm up, it was good, but as the data, more and more data got added, uh, you could see that the latency did never, it spiked but could never recover back, right? And the same thing here, it's more like a specific to P99, like the really the slowest of them all. They're all and the lower than the average, right, in terms of the throughput. So it seems like the throughput suffered uh, uh, because latency obviously is inversely proportional to throughput. So you saw a concentration of a whole lot here, right? So in net, this would be fine for some use cases. For example, if your latency requirements are, I can live with 10 seconds freshness, this is fine. Rising Wave Core should be fine for you. But what if you wanted below a second, right? Like under 100 millisecond. How would that look? So now that's what I'm gonna try to uh, reproduce. So I'm going to run the same workload now, but I will this time I'll set up, obviously I need to set up some parameters. So let me first, I need to modify this variable so that I know we're going to use Ultra. Okay. Now I set the environment variable that allows me um, uh, to use Ultra instead of standard. So I'm going to drop the database. You have to recreate the database again from scratch. And then I have to set a license key because this requires a license key. So I'm going to quickly open my database. I'm going to connect to the local database, and then I'll set I have to copy the license key. Okay, the license key is set. Now I'm going to create the objects like I did for last time. Okay, so it's going to create the brand new objects again. Now this is being created with Ultra. And I'm going to start the consumer just like I did last time. And then in parallel, I will run the producer. So the same thing we did last time, you'll see the same process playing out. While that's happening, let me uh, let me move these. Let me copy over these files to and call them, name them separately because they'll get overwritten. I'm going to call these two dashboards as a standard, as a yeah, these two files. I'm going to call them. I'll prefix them with standard as the name to make sure they don't get overwritten. Okay, so I have I'm going to compare these two files, standard latency throughput, standard detail analysis against the new ones that get generated after this run is complete. So the producer has finished creating the objects. Is actually, as you can see, it's faster with Ultra. The time it took to go through producer and finish processing. And on the consumer side, we're already halfway through. Um, it should take a few more seconds, and then we can generate the graphs to show the difference. Okay, as you can see, the latency, like previously when I said it was 2 to 3 seconds, here if you see, it's like really low, 20, like we're looking at like 20 milliseconds, right? So you can already see the at the granular each event level, you can see the difference of the in the performance. Okay, now let's copy over that data of the latency from the EC2 server down to this machine, and then we can plot the graph and see the difference. Okay, I got it. Now I'm going to run the Python program to plot the latency. Okay, now see this is running on Ultra. You can see the latency is pretty uniform at below like around 20. There are obviously there's a spike here. Seems like it went over 100 millisecond for just like a minute interval. But you can see if you compare that to the previous one where it went up to 1800 milliseconds, right, up to 2 seconds. Here we're talking less than one tenth. And as you can see, consistently it's around 20 to 30 milliseconds, which is incredible considering the amount of data we processed, like 10 million records. It's great. And also another thing, throughput, there was a lot of variability in the throughput with Rising Wave Standard. With Ultra, you can see pretty much a straight line. The only thing is that initial blip, we need to see what caused this, but otherwise it looks pretty straightforward, right? Um, and then in the details also, if you go through, you'll see that there is hardly any in P90. There's very little outliers. Pretty much very consistent performance. All of it is you look at average P50, P90, P95. In P99, maybe there is a little bit of scatter, but still very consistent. Very consistent, and also bulk of it is around 20 to 30, right? The outliers are there, maybe a few more on the 40 to 60, but otherwise pretty consistent. And look at this one. The throughput is like flat line. Amazing, right? And then also the correlation in terms of latency to throughput for P99, all concentrated around the same along the line that we expect, right? It's not below or above, it's just exactly where it is. And in terms of the spread for P90 to 99, there are some spikes, like the first one, there are three or four where you see some jaggedness, but in terms of the overall, like milliseconds, like 25, it is still within that acceptable range, right? So as you can see, this is all very it's a marked improvement over what you saw with this thing. Maybe if you really want to, maybe I can do a quick side-by-side comparison because that really brings in, sorry, maybe I'm going to open just this guy for now. Okay, it'll come up and then I will do the Ultra one also side by side so that you will see one over the other and it'll give you a much better view. Okay, so the first one is the standard and the second one is this thing. So let me put them side by side like this. The same workload, everything ran. Here it's going up to 8 seconds almost latency. And you see how it went up and came down and all that. Here you see the top line is 100 milliseconds. And that too, this is just a small outlier. The rest of it is all around 20, 30 milliseconds. So you'll see the just the difference in pure latency, right? So this is what is possible with RisingWave. And if you go on the throughput side also, you'll see that a lot of variation on throughput, and on the ultra side, it's pretty straight, right? So that's pretty much the demo. Um, and let me pause here and see if there are any questions. Okay, I don't see anything. You see, Yovana, on your side, questions? I know
No,
this is
but
a very technical
this
topic.
is all very detailed. So I think you've covered it all.
Yeah. Okay. If there are no questions, then let's stop here. Um, we'll send the slides and recording if you want to look at it. And if you want to try on your own, it's on a public repo. So uh, you can run the workload on your own and see if this is something that applies to one of your use cases. And we're happy to help you try and give you a trial license if you need for Rising Ultra. Okay. Thank you, everyone.